All right, welcome back everybody. Today we're going to be talking about applications of double integrals. All right, so as we start looking at these double integrals and we start looking at their applications, one of the things that I want you guys to recall is this topic that we learned back in Calc 2, which is learning how to compute the center of mass for a piece of lamina. All right, now this piece of lamina was just this either strip or this plate that we were going to find the center of measure for. All right, now when we go through and we find this measure of center, we needed three things. The first thing that we needed was we needed to know what was the mass of the lamina. All right, or the mass of that object. What was the moment about the x-axis and what was the moment about the y-axis? All right, so we needed to know those three things. All right, now if you need a quick refresher for how to calculate the center of mass using Calc 2, I'm going to put a card in the top right hand corner. You can click on that and it will take you over to the other YouTube video where I talk about Calc 2 center of mass. All right, but essentially the center of mass formulas are right here in orange, and those are going to be the formulas that we're going to be using to help us work with these double integrals and their applications. All right, so let's move on down to what we are going to need for this particular section. All right, so the new items that we're going to need. All right, now we're still going to be defining mass in the exact same way. All right, now if you notice back from Calc 2, when we were starting to define mass, back in Calc 2 we just said it was going to be the density of the object multiplied by the area that is making up that lamina. Now in this particular section in Calc 3, what we're going to do is we're going to consider the density not just to be a constant density, but here we're just going to make it a continuous density. That way we can model it by some sort of function for this piece of lamina. Right, so if the thickness is getting thicker on this piece of lamina, now we've added this third dimension or this third component to add or to contribute this sort of density into that equation. Now for the area of the lamina, well, we learned how to compute areas back in 15.1, 15.2. We learned that double integrals can calculate those areas, which makes sense to have this equation for mass. Now, we need the moments about the x-axis and we also need the moments about the y-axis. All right, so the moment about the x-axis, again, it's going to be defined in almost the identical, almost the exact same way. If we differentiate this, or if we find the antiderivative for this with respect to y, because these are both y values, then we naturally get that the antiderivative of 1/2 y squared is just going to be y, and that's right here. Same thing here, if we integrate this with respect to y, that means it's just a constant, which means we're going to have this moment of moment about the y-axis. Now remember, the moments about the y-axis, moments about the x-axis, just basically look at what was that average distance between the point and the average of that data set, or those x values or those y values. All right, now when we want to find the center of mass, we're still using the exact same equations. Again, it's just going to be a little twist that we're using the double integral version of this. All right, so we want to go ahead and jump into the problem set to use these double integrals to be able to find this center of mass for this given object. So let's go through. Here's your example. We want to find the center of mass of the lamina that occupies the triangular region enclosed by the lines y is equal to 0, y is equal to 2x, and x plus 2y is equal to 1. Alright, so we need to figure this out. Now, the first thing that I'm going to do is, looking at the double integrals, it's saying that I'm going to set up a double integral over some region D. Alright, so region D, that's going to be the region that I want to focus on. In other words, it's kind of acting as my domain for this function that I'm going to have to integrate over. So when I'm looking at this, I want to go ahead and I want to make sure I graph this. Alright, so let's try and sketch this domain, or this region D. Let's see if we can get this done. Don't mind my dog, she's just in the back. I don't know what she's doing. Oops. There we go. There we are. That's a little better. And let's get this going, 90 degrees. Alright, let's see. I'm probably going to want these a little bit less than that, or sorry, more than that. So let's go with 2, 4, and 6. And this will be just like that. Alright, so my first equation, y is equal to 0. So y is equal to 0, that's just going to be my horizontal line here. There we are. Alright, and again, this was, oops, excuse me. This was the x-axis, and this equation here was y is equal to 0. Now I'm going to get y is equal to 2x. So if x is 1, then y is 2, and if x is 2, then y must be 4. There we are. Alright, let's get a line going here. There we are, looking good. So this is the line y is equal to 2x. Alright, perfect. And now we're going to get the last line, and the last line was this x is x plus 2y is equal to 1, which I'm just going to go ahead and solve for y. That should be negative 1/2 x, and we're going to say this plus 1/2. Alright, so just making sure that was negative x minus 1 and then divide by 2, perfect. So at this point in time I have an x-intercept of 1/2. So there we are, my slope is negative, which means I'm going to be dropping down. So it's going to be down a slope of 1, so down a slope of 1, so that's going to be about here, and then over 2. That's going to look like it's right here. Perfect. Alright, let's go ahead and there we go. Perfect. Alright, so we have this equation already set for us. So this is x plus 2y is equal to 1. And the region that is being bounded is this region right in here. Awesome. Now, looking at that region, so I'm going to zoom in on this. So looking in at this region right in here, this is a region that I want to integrate. So because I want to integrate this specific region, I want you to pay attention to this. Say that if I were to do these vertical heights. If I were to do these vertical heights, I want you to notice this vertical height right here versus this vertical height here. Even though they have the same bottom y value, the top y value of this height is this purple line, and the top value of this height is this orange line. Which means if we set up a double integral for this region where we use vertical heights first, then that means we're going to have to set up 2 different types of double integrals being split right down the middle here. That way the triangle to the left will have the same height, the triangle to the right will have the same height. So 2 double integrals to find this mass, and then to find the moments that we need. Alright, that's kind of rough, it's kind of tough. Instead, can we think of horizontal heights. Notice anywhere that I draw this horizontal height within this region, the bottom part, or the leftmost, is always the purple equation. The rightmost is always the orange equation. And that's no matter where I draw this vertical height within this region. This means that setting up a double integral with horizontal heights is going to be the way to go. That's going to be what we want to do and how we want to work with this particular setup in this problem. Alright, so now that we got everything set, let's go ahead and let's start trying to set all this up. Alright, so I'm going to go with my mass. Here we go. And this is going to be the double integral, and I want to take these horizontal heights first. Alright, so when I'm looking at these horizontal heights first, that means I need to get some x values here. So I need to find out what is x equal to for this line. Well, for this line, x is equal to y over 2. For the orange line, x is equal to 1 minus 2y. So when I take these horizontal heights first, I'm going to go from left to right, which means the x value is y over 2. The top value is going to be 1 minus 2y. Alright, and that's these horizontal heights. Now my vertical heights are going to be moving within that region, which means I need to find a point of intersection. I need to find out what that is. In order to find that out, I need to set both of these functions equal to one another. Alright, let's go ahead and let's do that. Alright, chances are I'm looking for a y value because I'm looking for the point of intersection so that I can integrate with respect to y, because I already found my dx's. All I need to do is find my y values. Alright, so I'm going to set both of these x values equal to one another. So this is going to be y over 2 is going to be equal to 1 minus 2y. If we try to solve here, this will be y is equal to 2 minus 4y. Moving this over, we get 5y is equal to 2, which means y is equal to 2/5. So my y values, they are changing from 0 all the way to 2/5. And what we're doing is, if we were to leave it blank just like this, we would be finding this area for that region. But we're not trying to find the area, we're trying to find the center of mass. And in order to do that, we need to integrate with respect to the density, or sorry, not with respect to the density, but we need to integrate the density within that region. So the density within that region is just x. And the reason it's just x is because that's exactly what we were given at the beginning. We were given the density function, and that's what we're integrating over. Alright? Not just a region, but that region has that specific continuous density. Nice. Which means all we have to do at this point in time is we have to go through and solve this. Alright, now this should be a double integral that you all should be very familiar with in knowing how to solve. Alright, so I'm going to say I want you all to keep going. So I want you guys to try this. Make sure that you know how to solve this type of integral. And if you want, you can put pause, because I'm going to give you the answer in just a little bit. Alright, so the answer here should be 2 over 25. And this should be for the mass. Alright, now that we have the mass, let's try to find the moment about the x-axis. Alright, so let's look at those moments about the x-axis. The moments about the x-axis, this is going to be another double integral, but this time it's going to be a double integral over the region that we're looking at, its density, and it's going to multiply a y value. So it's going to multiply the density times a y value. So again, this first piece here, that's just your density function. And then it's going to multiply a y value. Oops, excuse me there. Trying to make that x look kind of nice. It's going to fail. There we go. So that density, and then moments about the x-axis, here we just multiply by the y value that we initially look at. All right. Now, again, double integral for that region. Since we already went through and we set up the double integral the first time, we just go through and we keep that exact same double integral. The only thing that's changing here is going to be that density and how we observe that density within that region. And that's why we just multiply it by y. All right. So again, we go through and we follow this process here. That was 1 minus 2y. Here we are. And so all we do is just evaluate this double integral here. And again, you can go ahead and evaluate this double integral, but one of the things that you're going to get, spoiler alert, so if you want to do this on your own, put pause. The answer is 7/50. Okay, not too bad. Again, once you set up the initial double integral, the rest of the double integrals are going to be almost identical, if not exactly the same. Let's find the moment about the y-axis. So finding the moment about the y-axis, again, we're going to need our density function. All right, here's the density function. And we're going to need to multiply by another x value, and that was because of our initial formula here. Moment about the y-axis is the density for how your x values are changing about your y-axis. All right, nice. And again, since we already set up our double integrals over here, I'm just going to keep using that exact same setup. 1 minus 2y, and then from 0 to 2/5. There we are. All I have to do at this point in time is integrate. And that's what I want you all to do. I want you to go ahead and integrate this and see what you get. So put pause, do the double integral, and then come back so I can tell you the answer. All right, I hope you all got these 3 answers. Now, all of these 3 answers are going to be used in order for us to then be able to calculate the center of mass. Now, the center of mass, that was this x bar divided by y bar, which this means that we're going to take the moments about the y-axis, and that's these guys right here. So it's going to be 31/750, and we're going to divide this by 2/25, which was the original mass of that object. Moment about the y-axis, we're going to take those moments about the y-axis, here we are, or sorry, moments, yeah, so for this, guys, we need the moments about the x-axis, that way we can get the y values. So that's 7/50 divided by 31, oops, excuse me, not 31, divided by 2/25, like such. And this should simplify real nice. The center of mass should be 31/60, comma 7/60. So here is your center of mass. And again, this is done with double integrals. And typically we want to use double integrals when our density is an actual continuous function. If your density is just a constant, then you can go back and you can use techniques based in Calc 2. But naturally, techniques in Calc 3 make it a little bit easier to work with, which is why we want to use these methods. All right, now let's check out one more topic that we're going to be looking at. All right, the next topic that we're going to be looking at within this section is going to be moment of inertia. In other words, known as your second moment. All right, so before we go, I'm going to put up some definitions, and I'm going to put up the formulas that we're going to be working, and then we'll go ahead and work with them. All right, so for these moments of mass, and again, we're going to need the moment of inertia. In other words, this is going to be looking at your second moment. We're going to be using this equation here for inertia, which is going to take the value of m, and it's going to be the mass of this object, and then we're going to have r, which is going to be the distance from the particle to the axis. And then the distance to the axis that we're going to be looking at is going to be either with respect to the x, y, or the origin. All right, so and as we start looking at this, the equations are given here. So we need the moment of inertia about the x-axis, moment of inertia about the y-axis, and then we're also going to be calculating the moment of inertia about the origin. But if you notice, the moment of inertia about the origin, that's just going to be the distance as we start looking, the distance for the x or the y to be close to the origin. That naturally is going to just be the equation of a circle, which we have that x squared plus y squared here. But notice it's just the addition of the previous two moments of inertia about the x-axis and about the y-axis. So as long as we're able to find the first two, then the third one shouldn't be too bad. All right. So for this example, we're going to want to find the moment of inertia, the three moments here, moment about the x-axis, about the y-axis, and then about the origin. And this is going to be for the previous example. All right. So this is for this previous example that we had here. So what I'm going to do is I'm just going to copy and paste this down there. That way we can work with it. There we are. I'm going to copy that. And let's put it down here. Let's paste it. Wow. Awesome. Whoa, where'd you go? All right, give me 1 second, everybody here. There we go, perfect. All right, so again, what I want to do is I want to find these moments of inertia. But notice, I've already set up my double integral over that region from last time. So when I set up these double integrals, the hardest part's already done because, again, we just did it on the other problem. So all I got to do is with the double integral, and this time I'm just going to use this y squared multiplied by my density function, where my density function here is just going to be x. All right, and then as we set it up last time, this was dx dy, and then we can go through the exact same integration process, right, like we did last time. Excuse me there, that was 1 minus 2y. Perfect, and then that was from 0 to 2/5. Moment of inertia about the y-axis, here we go. Again, same double integral from 0 to 2/5. Innermost integral, that's going to be from y over 2 to 1 minus 2y. And then I'm going to need my x squared multiplied by my density function. In this particular case, is just x. All right? And then this was dx dy once again. So once we're able to solve for both of these, and what I want you to do is I want you to solve for both of them, see if you can go through and evaluate them. So put pause on the video, get it done, and then come back and I'll give you the answer. And again, these answers are all on the honor system. I'm hoping that you are actually trying these before you come here and just say, oh, well, Mr. Castro is going to get me the answer in a little bit. I want you to give them a shot. Now, for the moment of inertia about the origin, all we have to do is take both of the moments that we just found and add them together. Once you do that, you're going to be left with the moment of inertia about the origin, which in this case should just be 2 over 75. All right, so there's the extent of the application problems that we are going to be looking at in this particular section. All right, so I hope you all enjoyed this video, and I will see you again soon for the next section.